The same way call is a potential blocking call, blocking service call. Potentially blocking service call. People will just say, oh, that's a blocking call, the category of this. The same post is not. Post never block. Okay. Well, when you block something coming out from the bathroom, you didn't clean it, it cannot come out. So, if it's going to release Semaphore very happily, allow it. We don't block the process. OS does not block post service. It's not blocking service, but this is a blocking service. Blocking service, in this case, is potentially blocking, depends on the control value. So when a semaphore is initialized, the control value is the first set. Okay, the control value does not need to set from 1 or above 0. The control value could set from 0, even -1 sometimes. Okay, for the purpose of the control. Does that make sense? Like using like pizza is a semaphore that starts from 0. Okay, consumer just waiting for pizza. The value is 0 right now. Everybody calls same post, waited. Yeah, it's a line out for pizza waiting, and then they've got semaphore control value is 0. And there's a producer, yeah, those are consumer. Producer will increment the value whenever you finish busy baking one pizza. It will increment the value, and then to 1, and then so the producer will call same post on the pizza semaphore. So the kernel is the third guy that serves same way, same post, and then will release one person to proceed the code, which is to access the pizza data. And then, when that person finishes accessing the pizza data, it will send post, then we'll release the next one. Okay. But at that time, if the value is 0, then that person still waits. Okay. So it could be a producer over here, multiple consumers over there. Okay. So they compete to increment the values from here and decrement the values from here. So the control value in the semaphore becomes the count of the number of available pizza. Okay, there's one way to do that. Another way to do that is like this. All right, there are 2 groups of processes. They all same way, same post. That group is the consumers. All want to take a pizza out of the pizza count. And then over this side can also have a group of processes. They also do the same way, same post. But in between is to make pizza. Okay, make pizza. And they want to increment the count guarded by the same way, same post to increment the pizza. Okay? So let me write it out. So here is the consumer. Consumer's code. Consumer's duty is to pizza. How do you spell pizza? Pizza minus. Okay, and then you have the code here for this producer. Okay, so this is semaphore pizza. It's a pizza plus. So this is a common variable, one variable. Okay, we cannot allow multi-accessing of that; it will be inconsistent. So it's got to be guarded by the same way, same post for the producers and the consumers. Could be multiple, doesn't need to be 1. Okay, could be 0, could be multiple consumers and producers. Okay. All right. So this pizza is a single variable, got to be guarded, like we said. When it sees it, it has to use it, test and set. That's not gonna happen unless there's a test set guarantee the atomicity, the 2 steps. guarded by the semaphore. Okay, make sense? Yeah. If it still doesn't make sense, then how about refrigerator? You have one refrigerator. The door is kind of small. You want to get a cold beer. You open the door. Another person should not like squeeze in. Or nicely way behind, right? If that person also need to access the fridge. So one person at a time, same way, same pose. Does that make sense? All right. For larger refrigerator, you may have two person looking, which you have a semaphore initial value too. You open one door, there are two doors. You open this side, and that side can still be open, so it's down to 0 now, 210. So the other people will start to wait. All right. But those are the protocol. People say, oh, that's the application protocol. They need to use semaphores. Okay. So who's going to enforce the using of semaphore is not the OS. It's the application developer. They got to use them correctly. And they can be used in a nested fashion, just like everything else, like loops. Okay. There could be two semaphores. Same way, okay, same pose. You say, why? Well, just kind of like double door building. You have one door, you got to get in, and then you have to get in another door before you finally get the pizza. You come out, you got the same pose two door. Does that make sense? And the room has a capacity says maximum 2 person, inside. But that's kind of a small house, yeah. Most buildings says maximum 200. Okay. But who's going to enforce that? So there will be two semaphore services. One is a CSUS Weide, and this is a CSS call, API call. One is the CSS same post, okay. Same syntax. They all require the semaphore number to be passed to the kernel, and the service number. That's the okay. Then the kernel can know what service and then why is the semaphore number to be checked. And the service code in the service.c is the same way service and the same post service. They will work on the semaphore. The real work is in the services.c that contains these services. And so what about the real OS? The real OS, you have a system 5 IPC services, including the semaphores here. And they are not part of the process resources. They are separated. So you can see IPCS is the shell command, the status of the IPC on the system right now regarding the shared memory segment, semaphore arrays, and message queues. And the keys must be given to processes to access the semaphore or shared memory or message queue. So the owner is the creator of the service, and it will be it will pass along the ID and the key to processes that are allowed to use semaphores that it creates. Okay. So here we use the semaphore number. Basically, the meaning is a key. Look at Athena, a lot of people there. Probably there's some residue. Root amount, semaphore. So typically people run some application that calls the semaphore services but didn't clean up. And then you have the residue until the system reboots. Then that semaphore array will be still occupied, will be still there, occupy the one of the semaphore resources. And if you look at the host that cater services like Oracle database engines, then there will be tons of semaphores and message queues being used by the applications. The process is coded by application developers. They use Semaphore message queue to share memory management to do things. Or if you program CSC60, you already know that how to use these, and they will make the system having shown up the status of the IPC right now. Okay. Okay, so what do you think about the sys calls? So very simply, this phase is actually not too hard to do. You just need to create your own sys calls and link to the services. Okay. So the sys calls is the code that need to put in the two things to the kernel to receive through the CPU registers. We want to, this is the user prompt. User prompt calls the sys same way with this syntax, standard out. And then it calls the sys same post, standard out. Same syntax. So therefore, they become the subroutine of the user process. And then what does it do? It will put the service number into ECS register, and then put the standard out, which is Semaphore ID. We're just going to use the standard out as a Semaphore ID into ECS. And then call the interrupt 128. Okay. You say call or kind of like execute. And there's no return. Okay. After the interrupt 128, there are nothing coming up. Okay. And this is exactly the same. I shouldn't say that. This service number is a little different. So the service number, this one is the same way. And then except the service number. Put the sys same post service number into the EX. The same for the rest. Okay, so this is the only difference. Of course, kernel's got to differentiate the two somewhere. Yeah? So where does it go to? What's this? Yeah. Interrupt 128 will go to entry.s. And then goes to kernel, and then kernel call the syscall service. Syscall service will check the EAX, which is the service number, and then go to the service code. The service code will be a new one. Okay. So eventually this will come to the service code. Okay. The service code is described here, same way service. Okay. Same service. Same service will receive the semaphore number. Okay. This is given by the sys service code in the sys in service.c. So this becomes a new function in the service.c, being called by the sys service, syscall service. Syscall service. Okay. So the via syscall service, and that calls, because it checks the service code. Okay. The service number is sys send wait. Then by service number, it calls this. So indirectly, okay, comes in like that. And then what does it do? Same way, check the value greater than 0. The semaphore value greater than 0. It will down count it. Okay. Value minus. Else what? Else we need to block. Okay, block the column. The call process PID is the rump hit. So that means there are 3 things to do when we block. 1, 2, 3. Okay. One is the rump hit is going to go into the wait queue. Okay, the wait queue of the semaphore. Okay, wait queue of semaphore, and the state is going to change. Okay. So the process state is going to change. It's going to be downgraded to wait, and then the rump hit is no longer running, so it's going to be reset to -1. Okay, so then the process scheduler sees that, we'll find another one, okay, from the ready pick queue, or set it to 0. Okay, so that's just it. Okay. And then the other service by service number is this one. Okay, different service number. Says the same post. Says same post, then the service to call is the same post, the service. Same post service is going to get the information of the semaphore number, and then it will check using that semaphore. Okay, using that semaphore, and to check wait queue. Okay, this time instead of checking value, it will check if the wait queue on the semaphore is empty. Okay, empty. You know what empty means, right? Means the size is 0. And then the upcount value, okay? Value upcount. Else wait queue is not empty. Okay, then you got your hands full. Wait queue is not empty. There are actually people waiting. What are you gonna do? Yeah. To do what? So instead of blocking, okay, it's the opposite of blocking. Release, okay, release the first waiting process. So the first waiting process will be released, dequeued from the wait queue of the semaphore, and move to the ready pick queue and state change. Okay, so there are 3 things to do. 1, 2, 3. Also, 3 things to do. Like I just said, take it out from the wait queue, move it to the ready pick queue, upgrade its state. Okay. You gotta get familiar with these things, okay? Otherwise, that's in this way, a waiting process. What does that mean? Should I put it on the Facebook? Or blocking the running process? What does that mean? So this should check your understanding about what does it mean. Okay, what's the blocking? What's the running process? What do you mean by blocking? Where should I move it? The kernel service should move it, and then state change. What states are there? Yeah. So there are 50 United States. Which state should I change it to? Okay. so there are only a few states that in the code that you can take a look. Okay. But the process state in 139, you probably started from 7 states. A lot of states, but we don't have that many. Okay, the coding ends. Alright. The new prod.c has a new version of user prod. I show you that, and then run it. And one is the demo node sim. One is demo sim. And demo sim is the target we want the new prod, the user prod to do. So press N key a few times when you run the demo or test your own. The new constants says same way, says send post to 2 services, then 2 new constants. And then semaphore type. Oh, why is the semaphore again? What does semaphore have? 2 things. Yeah? Sema and for. True, false. Is that a new kind of gourmet dinner? Semaphore. There's a number, a value, control value, and the wait queue. And the semaphore we want to control about is actually needs to be created as a global data. It's called a video sim. We have a semaphore type we want to apply to the video sim. And that's when standard out is being called for, same way, same post. The operation is actually checking into the video sim. This semaphore that has 2 things. Okay? We need to declare semaphore resources. The system has a video semaphore for it, for the display. And like IPCS, you saw there's a system assigned array, huge array of semaphores assigned to user. User requests a semaphore, brand new semaphore, kind of like brand new car. Why is it for? Why is it called? It has no name. Don't know what application is going to use it for. Okay, so that's the IPC resources that the OS has. Okay, being given out for usage. So here our OS also has one created called video sim. Video sim. So to be more precise, okay, it actually follows it. And then during the OS boot, we're going to set the video semaphore with the value 1, and then empty the wait queue. Wait queue has no waiting processes initially. Okay, so the semaphore is ready, and okay, so the new syscalls are the same way as the post syscall. Need to, like I said, put into the EAX and EBX the 2 numbers. 2 numbers. All right. Pass their service and semaphore numbers via CPU registers to make the interrupt 128. Okay.
So now you get a feeling about what syscalls are. Syscalls are not very smart things. It's kind of like process needs kernel service. How are we going to, let the kernel know what process it is and what kind of arguments we want the kernel to get to process that service? Okay. All through CPU registers. Oh my gosh, what does that mean? That means that your process is running here, and then the process need request service. Okay. The government, OS is the government. So, I need to request the big trees in front of my house that fell on my driveway, on the road. So how are you going to go to government? You call them, you write mail to them, you knock on their door, you protest, or what? No, you gotta get naked. What does that mean? You cannot carry anything with you. What? Now how am I going to? And then you're going to go in cold, in the traffic. You're going to be frozen. And then how am I going to send a service? In your cavities. Oh my gosh, I got to start a service number in my mouth. I got to start other arguments in cavities in my body, so go in because of naked CPU. And the CPU is going to be checked at register numbers, and that indicates service number and my address to remove the tree. Does that make sense? So you see, that's what the syscalls are. Okay, and when you come back, if it's get PID call, somewhere there's a PID in your cavities. Which one? Is it in my ear? Okay. All right, you still don't see the humor here, then you're missing something, okay? You got to study. If you study, then you understand that humor. It's all computer nerd humor, okay? So if you don't understand it, that you are not a computer major, okay? All right. So you cannot carry anything with you. No paper, no briefcase, no envelope, nothing. You got to go in naked on the CPU registers, the CPU itself. And then the 7, program into services, the new services. So you can see the syscall will trigger interrupt 128, and CPU will jump to IDT entry 128, which is a syscall entry, and then go into the kernel, with the traffic being examined by the kernel, okay? And then there are register values to know, what service to do. So in service.c, the new service is going to be same way service as the same post service. The pseudocode I just wrote down here. Okay, so this is the last thing, then we'll take a break. So this is actually the same pseudocode I just wrote. If the service number is standard out, I didn't write that one, okay, so you need to have that one. If the same number is standard out, apply to standard out, the video semaphore is the one to check, okay, it's not standard out. It's a semaphore. Standard out is a key to lead to the video semaphore. And then we check the value greater than 0, no problem, just uncount it, so the process doesn't need to be blocked. The process can continue the statement after the same way. Yeah, that's to start to get into the critical session. Else, it's 0, it's not greater than 0. Then we need to block the running process by doing the 1, 2, 3 thing, okay? And still else, meaning that the semaphore number is wrong. This one you shouldn't need to program it, but for the safety, you can program it, okay? This else is from, this else, okay? If the semaphore number is standard out, if the semaphore number, right now there's only one possibility, the semaphore number must be standard out. If it's not, probably your syscall is not written correctly. So the semaphore number is not sent over the standard out is not sent over. Okay. So basically, this is the kernel error. Semaphore service also operates on standard out only. The semaphore number passed over, and that passed by the traffic EBX. And then the wait queue, check the wait queue, empty, then just outcount the semaphore value. Kind of like, oh, Tom comes out from the bathroom, calls same post, but there's nobody waiting. So the control value changes from 0 to 1, 0 to 1. So in the future, anyone can also pass that one without being blocked. Else, we got to liberate or release a waiting process, doing the 1, 2, 3. Okay? Does that make sense?
Mm-hmm.
You should ask one question: is that control value, when someone has been weighted with, don't touch that, leave that thing 0. Because if you raise it, then you still have to down count. Okay. Kind of like a key. Say, actually, it's just the one key people put on the table, and then you get to open the door and go in. You lock it from inside, and then take the key, put it on the table. But if there's a waiting person, you will grab the key again, so it still becomes 0. Okay, so that is 0 and 1 thing. Okay. Starting from one key, it will always either be 1 or 0. It could not be 2. That would be a big problem. If one key becomes 2 key, that would be funny. You go in, lock, and then another person see, oh, second key, also go in, and then they sit down. Then you will be stacking, on each other's lap. And the human, of course, can see that, but process cannot see that. Okay, they'll be stacking each other up on top of the toilet. That'll be fun. All right. And the ACE is just the user process I started from the beginning. Okay, so let's take a break. Because a lot of people, don't understand because they didn't understand from the beginning. Phase 1 is very difficult to understand if they miss the time of lab. So that's the.
Do you have a grader?
No, I don't have a grader.
Do you want one?
What do you recommend?
Me, myself, and
No, I don't have one. The 159 is such a class that capable people already have work or are going to graduate. So in a semester, so good 159ers are always
hard to find.
always loaded with work. And the bad ones doesn't work. So frankly, that's the thing, 159 it's like this, and everybody knows. So this is the class that really tests people that what other classes before this class that you have taken them and did well. So just time for you to have a chance to ask if you have any questions, or you just hacking around, don't have questions. Because I know that the culture that you are getting used to is that basically is search everything on the web and then you get them put together, it works. This becomes a big pitfall right now.
because the tools you use are already made for you, easy to use. So gradually CPE is not really building everything from scratch anymore. It becomes like, depends on those tools, that frameworks and whatnot, other people already built for you. And that becomes the wrong direction we're getting into. In the early days, that when you start from try out the micro mouse, every component you build, the power unit and whatnot, the circuit board. And right now it's just Raspberry Pi, it's already there, $40, $60 that can do everything for you. Then what do you do? How do you build that Raspberry Pi? That's the question. So every time I use a tool, you gotta ask yourself, how is it built? We use the virtual machine thing is also a pitfall. And how is that, virtual box built? We never talked about that. And take it off the shelf, then we start using it. And try to convince ourselves we are doing what we need to do to learn things. And actually, we followed a lot of other people's doing, because that virtual machine is not correct. There's no correct timing control. But one thing, they're missing pieces, so it's not real in a sense. It's more tolerable, more forgiving in a sense. The tools they use are beautiful for your practice. So when the tools become too convenient, and then that becomes a problem. Yeah? And we're going to expand from the semaphores for the device drivers. Okay, so we're going to start to delve into the device drivers soon. So what do you know about device drivers? Okay, so phase 4, we're going to have the interrupt-driven I/O devices, such like terminals. All right, so this is the TTY teletype. Teletype writers. Telecommunication typewriters. It's not talk to you later. Okay, TTY. And then becomes the software terminals. So right now, PuTTY and the software terminal used on the Mac, it comes from the originally hardware terminals. And you can see the TTY right there, PTS 0, PTS 1, PTS 2. So those are pseudo terminals. Serial port 0, 1, 2. So they're all under in the slash device here. As you can see the expansion of the devices. All the devices are treated like file access. They all map into the file system to be read, to be written to, like a file buffer. So standard in, standard out. You can see standard error is linked to my shell. This is the 3 processes, and there's printers typically like line printer 0, 1, 2, 3. And there are all the TTYs that's currently on the system. Some owned by me. Once I log in, that buffer will be assigned to me. And there will be
solid state devices, SDA. So it's adding more and more of different types now, besides the CD1 from the beginning, etc. What am I looking for? Data. All right, so beginning of the learning devices from the very simple process self of FD012. This is the new Linux convention. So in the process table, the system process table, this is the login user FD file descriptor 012. The file number is 012. The name is standard in, standard out, standard air, as you know that. What you learn process runtime CSC60. So all the processes are listed here by PID, just like they are directories. So this is inherited from the Unix convention. As a file system, the devices and process runtimes are also treated into the file system to be physically linked there. These are the users. It's a standard in, standard out, standard air. And mine is here. This is my process. So 3635, 3636, 5914. So what we're going to do is that the terminal is linked to the port of the target PC. And the two ports are serial ports. Connected by serial line. The data communication is a serial one. So there's a send one, bit by bit. Okay. Transmit over from this direction to that direction. And there's one bit by bit to be received to the target PC. On the other end is receiving and sending. Send receives, it depends on which side you look at. So it's bit by bit, that's why it's called a serial device. If it's multi-bit at a time, it's not serial devices. Okay. And these days, serial devices is the easiest to transmit file. That's why everything is on serial, including the Ethernet, the network protocol, etc., etc. What's not serial is in the early days, the printing. You got GPIC, general purpose GPIO port, and they are parallel. Multi-bit can be sent at the same time. You can configure it any way you like. Okay. General purpose IO. And that's way back. That's from DoD, military invention. Okay. That's just it. That's still the best communication protocol to be freely configured. Okay. But we're talking about very simple one like USB or like printing, we have the LPD. Centronic parallel. Okay, that's the company called Centronic. Parallel port. So that's a parallel wire can send multi-bit at a time, like 7 bits of data at a time. And there are other control wires, the total number is 35 pins. And then for serial port, first installation was 25 pins. It can be down to 3 wires. Okay, so it can be trimmed down to only 3 wires to do. USB is based on this universal serial bus that the Intel has patent as the protocol. As you can tell by the pin out inside the USB port. 4 contacts, okay, and then the shielding on the outside. And then what that means that is, okay, then you had send receive, you had a send receive ground, the signal ground. And then you have power, okay, so that's the voltage, high power, the power, and then this is the protected ground, the power ground, the big ground. So basically that's the serial port from way back, okay. And it's smarter in the sense that the device drivers are smarter. It's not that a connector is any smart. It's just a 4-wire connector. You can make it yourself. And we used to make these connection cables ourselves. A serial cable was something like $20, $30 a piece. These days they're just laying out everywhere. All the cables, nobody wants. So, students wire ourselves with telephone wires and whatever copper wires you can have. So that what that means that you got to study the fundamental of the data communications. And then things like clear to send, request to send, the timing, the baud rate, all kinds of jargon, data terminal ready, data set ready, as you do senior project. You have to deal with the communication parametrics sometimes. When you understand that, you really understand the data communication, how it works. And then later on, the expansion of the technology and telecommunication, it's really easy to understand. Okay? If you don't have that fundamental, it's difficult. Anyway, so we had serial port like this. Typically, you had a DCE, data computer end, and data terminal end, because the wire names are different. So the DTE size receive. This is the send. Data communication equipment end. Data communication equipment. Data terminal equipment. Data communication equipment end. This is send. This is receive. Kind of like that is the base. Okay. As you can know, that's the reason why you hardly see gender mutual connector, or even the sizes are different, the USB port, and larger size to the small and the AV, micro AV, and they will never be the same, like an extension. Okay? And that will cause the short circuit and the feedback. So it's got to differentiate this, and then that's why you have a USB hub. Okay. So USB hub, then the one side is uplink, this is downlink, and that's based on this idea of DTE, DCE relationship. Okay. And the wires start to cross, okay, so that you will have the same protocol, and then basically both sides are DCE. And later on, the device and both sides are smart. And then the send is send pin. Pin out on the port will be the same. Before you had 2 types of pin out because the wire didn't cross. Yeah. And then now you cross the wires, become 2 sides, the port pin assignment must be the same. Okay, both are send and both are receive. Right? Mm-hmm. Okay. So that's called a crossbar, the non-modern. Okay. So that's the convention they call the simplest fix of the module demodulation through the crossing of the send and receive wires. So both sides are BCE pinout. So there will be no complication. Okay. So both sides are hardware ports, serial ports. Serial ports has the built-in hardware protocols among them, just like C port from Alameda to Shanghai, from Beijing to Long Beach. Okay, so they will operate once you turn them on, get them power. They will operate by themselves. When they are turned on, they will send to the other side ready signal. Okay, the ready signal. If they just buy 3 wires, they can still send out the software packet, kind of like a packet, and the software serial signals, the bit zeros and ones, in like a data sent over that can constitute the signal called ready. Otherwise, you have to use the full-fledged 25 pin. Each pin is designated for that purpose. So, things are request to send, the clear to send from one side, send to the other side, and data set ready, data terminal ready. It's on this side. So data set ready is that the data register is ready to send, has data to send. And then data terminal ready is the receiving side, the data register ready to receive. And then this is through the shift register to shift the bit out, and then the shift bit in. Okay, it's the shifting of bits in one byte buffer between ports. So request to send, then clear to send is another pin or pin out, another set of signal of the software composite data packet. That's the signal name. And data set ready, data terminal ready, and then you start to send. Okay. So when sending, it has a speed. Sending speed preset, say 9600 baud. Baud is a person's name. So that means that sample rate is 9600 per second. Sampling this wire. Sampling rate. You oversample, then you double the size of the data, but it's not true. You undersample, then you will lose the resolution of data. You're missing the bits. So that is both sides need to be set correctly beforehand. That's a condition of the both side software has agreement by human. Say I'm going to use 9600, and that side you also use 9600, and then we're going to have this communication speed to be sampled. Okay, and then the sample bit by bit is not all data, because then you have the convention like 7-1E. So that's a 7-bit data. After 7 data bits, 1 stop bit, and then 1 even parity check bit. Okay, so that the sending is every 7 data bit, there will be 1 pause in the sampling, and then followed by either 0 or 1 to make the total occurrences of 1 becomes even in the data bit. Okay, including the data bit. If the data bit has three ones, 7-bit data has 3 ones, then you will add another one to make even number of ones. If it has 4, then this will send a 0 to not change that. Okay. And this can be set differently. Besides the baud rate, this one can be set differently. You can have 2 0 stop bit. This can be odd or even.
parity check. The data bit can be 6, 5, or 7 data bit. For YouTube conversion, 7 data bit or 8 data bit. So that also part of the 9600 sample. Bit sample. All right. So device driver's job is to make the serial port work efficiently, correctly. Okay. So this target PC here, if you have a software process running here, okay, they all run here anyway. So if you have a user process that want to send something to the display over here, okay, and then it's gonna be sent bit by bit over, bit by bit over. So we got a buffer what needs to be processed here, and then bit by bit sent over here. When this is received, it will respond, and then the next bit will come. So there's got to be a flow control. Flow control. Okay. So over the target PC side, there must be a buffer, okay, for the process to send out a string, okay, a 5x5 data. And this will be coming to the port 5x5, and then connect to the remote port, receive them 5x5. Okay. 5x5. The port themselves operates in bits. Okay. Port can automate the operation of the bit translation once you give it a byte. Okay. This is many bytes. So this is the idea. The port does the bit by bit sending, okay, and the receiving here. The hardware terminal after receive will display onto the display memory, like the VGA memory you have made to show the display. Okay. That will be displayed here onto the display. Okay, so this is building in the hardware. We don't need to write anything about it here. That's hardware built in. From the receiving port of itself, it will display what's there, and then the cursor will move to the next. Okay. And the ASCII code will tell this what to do. Okay. Is it byte space or what? Okay, so that's the idea of the terminal display. So how do we know in this case if this is a device driver process? Yeah.
Mm-hmm.
It needs to know with the semaphore and with the flag that the port can be sent with another byte from here, the buffer. So this must be a pointer to the buffer, which byte to write to the port using the RB function. So as you know that we have inbuilt an RB function, and these are the two CPU registers access mapped I/O.
Mm-hmm.
Okay, so that's the idea. So where's the I/O number? I/O number of say serial port 2FA. So that's the I/O number, and the character put into another register
So this one put into EAX, and then the EBX will be the next character to be displayed. Okay, out B. In B is to read the keyboard. When the keyboard has input, and it will be sent over from that port to this port. And then in B, we'll read from the 2FA. It's the same port number. So there will be an event that caused the flag to raise. So this is the semaphore that tells the process the event has occurred. And then the semaphore can do action, the device driver that is. And depends on the semaphore to do action. So there will be a write semaphore telling the device driver writing is available. So the characters can be output to the port that's connected to the terminal. So this is the target PC side, and that's the terminal side. And this is the cabling. All right. So the insertion of the signal comes in. When the port triggers the signal, and that's the interrupt request number 3. Timer is interrupt request 0. The serial port is interrupt request 3. And this will set the flag up by the handler, the service code. Well, timer service code, we can also have the interrupt request service code for this. Okay. And whenever that event happens, it's kind of like timer event. It's asynchronous to the device driver code. Okay. And this will trigger the device driver to execute its code and then causing the output on the next character to the port. And then the port will feed back with IRQ3. So this is the interrupt driven output. Okay. It's not busy wait, interrupt driven output. So whenever the device driver sends out one character, device driver can go to sleep, can be excused. Okay. And then the CPU can run other processes, other user processes. Okay. So it's not busy wait. If it's busy wait, this device driver is going to read holding the semaphore all the time. Okay, until semaphore indicates otherwise. All right, makes sense? All right, so that's the event. Now the keyboard event is also a type of event. Okay, keyboard, if you push the keyboard on the terminal side, it needs to be received over here once you enter, once you push on the keyboard. That will trigger the event as well. And the device driver will know by reading the status in the port. Okay. Reading the status in the port is an event, keyboard has something arrived, pushed and arrived. And so this will be read out and put into the, put into the buffer from this one here. From this one here, put into the keyboard buffer. Bytes. Okay, so when you type in, it's going to be queued in here. And when you display, it's going to be queued in here. So this is the display buffer. And that one is the keyboard buffer. So you got to have two buffers. Okay, two buffers. So the IRQ event is different. IRQ event triggers the device driver to do different things. One type of event is terminal has keyboard character arrived. One event is the terminal is ready to show another character, to display another character. Does that make sense?
Mm-hmm.
All right. Okay. So that's the interface. Okay, that's the interface. We're going to have the keyboard buffer, and we're going to have the display buffer for one terminal. Okay. And the device driver over here, device driver code. And this is the interface. And we're going to have semaphores. Why is that? Because the semaphore is the one that can do the flow control of the thing. Okay. When device driver has a string to display, okay, hello world, to the terminal, device driver will need to put them into the display buffer. But it needs to same way. Okay. Same way first on the display buffer. Okay. Display buffer. And if it can pass this point, it may get blocked. If it pass this point, it will transmit. It will put NQ. Okay. It will NQ one character from the hello world string. Okay, one character into here. So the hello world string can then be put in here. All right. What do you think the initial control value is for the display buffer? For every character, it will call the same way. And the initial variable control value of the semaphore for the display is the size of the display. Okay. So this buffer size is the initial value of the semaphore that guards this. Okay. Why is that? Because this could be very small and this could be very big. And this can run really fast and then put everything in. It's full. Then the semaphore value will become 0. Okay. When full. Yeah, initially is size, but becomes 0 when full. Yeah, because it's all being called by same way in a loop to display on the string every character by looping through it. All right, does that make sense?
Mm-hmm.
And then over this side is the counterpart of the device driver. What is this one? This one is the surface. This one is the terminal surface. Okay, in the surface.c. So the surface code is triggered by event. Okay, event is when terminal says, "I'm ready for display next character," or "I'm hungry for next character to display." How about that? You know, I need a character to be displayed. All right, so that display will trigger the terminal service. Display is ready. So the terminal service will take one character from the buffer. I'll be one character from display buffer. Yeah? And then send post. Alright, here is the guy that does the send post. That one is send wait. Alright, so this one is gonna send post. Okay, Semaphore post. On the display. Semaphore. Okay. So you see, this is the counterpart here. Here's the same way on the display semaphore. And here's the same post of the display semaphore. So because it reduced the number of characters in the display buffer by sending it to the terminal. Okay. So I'll be one character from the display buffer. So you reduce display buffer by one. Alright. And this will release this device driver process because it was waited when it runs out the display buffer. Does that make sense? All right, when keyboard has event, it's the other way around. The terminal service will in B one character. Okay. And the keyboard input. And then you will enqueue it to the keyboard buffer. Okay. Enqueue it to the keyboard buffer. And you will send post. Okay. You will do the send post on the keyboard semaphore. Alright. So this is the same post. So the keyboard buffer will have the keyboard semaphore posted. The value will be ++. That indicates how many characters have been typed in. Right? Am I talking to myself or is it totally futile? If it's totally futile, we just go home.
I think everyone's just tired today because of the career fair and all.
So the device driver will DQ the keyboard buffer. Okay. Device driver can DQ the keyboard buffer and then give it to whatever process requests for it. Okay. The keyboard string. The display string. Alright. So you see that's the but when this gets the keyboard buffer, it will send wait. Okay, it says send wait on the keyboard semaphore. Says somewhere on keyboard semaphore. So they can get one character out because initially the keyboard semaphore value 0. Initial value is 0, meaning that the keyboard buffer is empty until it's put in new characters by the terminal service, triggered by the event from the terminal port, and reading the input in B from the port IO X to FA. And then that will be enqueued to the keyboard buffer data structure is a character queue. And send post on the keyboard semaphore. Device driver, on the other hand, same way on the keyboard semaphore. Opposite of the send post here. Okay, if you can pass this point, meaning that there is a value greater than 0, then there is more than empty buffer. Okay, so it will DQ the keyboard buffer, okay, and give it to the process that access for keyboard input of the terminal. Okay, that's it. Any question? All right, no question. Then I guess we can wrap up early today because we are all tired.